Hi, thanks, Amalas. Hi, everyone. Very glad to be here to present our research on the influence of motion waveforms on the building peak and residual drifts, and also some practical implications for the damage state assessments using FEMA. In the earlier sessions, there are really concerns raised about how to control the residual drifts during the past Berkeley earthquake. And also during the last session, Professor Masala gave a talk about how the damage state of the building bridge piers are related to the drifts of the pier itself. So this states to the relevance of understanding this building response type, building drift responses in terms of damage assessments. This work was done with my colleagues at the Lawrence Berkeley National Lab, Konstantinos and Mamoun, and also Dr. David McCallum. And I would like to acknowledge the support from the DOE office CESAR office for their support. And also we have also benefited from the earlier developments of the computational tools we used from the EC computing project. So devastating earthquakes typically incurs significant damage to existing structures. I'm showing here just some examples of damaged structures, including buildings and bridges in past earthquakes. And one common lesson that we learned from these earthquakes or damaged structures is that they not only can suffer from a severe response during the shaking, but also they can be permanently tilted after the shaking. And this permanent deformation has posed a significant difficult decision for owners and stakeholders to make the decision about whether they should repair these structures or demolish them totally and just build new ones. So as engineers, we use two proxy measures, including the peak and residual drifts for building structures to control the structural behavior during and after ground shaking. So I think many of you are familiar with this story drift reminds, but I'd like to just bring us on the same page. The story drift is simply a measure of the relative deformation within a story of the building, and it's defined as the lateral interstory drift to the whole story height, and the peak story drift is simply the peak value of the whole time history of the story drift during the ground shaking. And the residual drift is the permanent deformation that exists in the structure after the ground shaking. And these two measures are considered effective because the peak drift controls the maximum deformation. So we can control whether the structure is collapsed, which is the main design focus for the current design codes. And the residual drift controls the post-event safety and whether it's repaired or not. So as we move towards the more resilient structures, this has gained more attention to engineers. These two types of drift demands has been used in different design codes and guidelines. For example, in SE 43, which is a design code for nuclear facilities, it uses the peak drift to define the 4 limit states, ranging from limit state D, which is associated with essentially elastic behavior for the structures during the earthquake, to limit state A, with large permanent distortion expected in the structure. And for different type of building systems, the limit thresholds are different. For example, for ductile steel moment frames, the structure would consider to be essentially elastic when the peak drift along the building, inside the building, is within 0.5%. Above that, this is considered the damage will start to accumulate. The FEMA P-58 document is a performance-based design guideline, which uses the residual story drift to define the damage states. As I show here, 4 damage states from damage state 1, essentially with no structural repair needed, to damage state 4, which is considered in danger of collapse. For example, for steel moment frame buildings, the the structure would be considered no repair is needed when the residual drift is below 0.2%. And above that, there need to be different levels of structural alignment or the repairs needed in the structure if they can be repaired. Otherwise, they will just be demolished. And also there is empirical relation in the FEMA documents that correlates the peak and the residual story drifts, which is essentially a piecewise linear function of the ductility demand in the structure. And using this relation, we can estimate the expected residual drift in the building based on the peak drift ratio in the structure. This helps a lot in the design stage. And optionally, we can consider a log normal space standard deviation of about 0.8 in the design process. So since this duration is intentionally simplistic, we want to understand in this study how effective is this relationship, and further, more broadly, what are some of the implications of using the residual drift to assess the damage states of the earthquake. So for this algorithm purpose, we have considered a suite of contemporary building models, including both steel and concrete moment frames. The nonlinearity of the buildings are modeled based on either detailed fiber section-based models or hinge type of models that considers strength and stiffness degradation. And for the input motions to the buildings come from the SGMD database, which enables us to do detailed building analysis with high spatial resolution in the near field. And considering there are over like 50 realizations for over 2,000 sites, and each with 2 horizontal directions, and we have like 6 buildings. So this results in over 1 million nonlinear response history analysis. And this is not possible without the computing resources. Before we dive into the results, we did some confidence building to make sure that our results are representative. So here, these 2 plots show some example comparisons of the waveforms that we got from our simulated motions and some recorded motions, and also the distribution of pulse periods, especially for the near fault motions, which are relevant and also of particular interest. So the observation is that they show similar pulse characteristics. In terms of building response, our structure behaves similarly under recorded motions and simulated motions. And also our data compares reasonably with the data points that is in the existing literature. Although the main difference is that we have a much large data density because of the availability of motions from the SGMD. So let's dive into the main observations that we have. So in terms of building peak drifts, we find that it's generally well correlated with the common intensity measures. So I'm showing here the peak story drift, correlation between the peak story drift and the peak ground velocity, or the PGV, and also the average spectral acceleration within a certain period range. So the R-squared values are relatively high, over 0.8, and the standard deviation is lower than 0.3 for our data. So this indicates good correlation between the peak drift demands in the structure and the intensity measure. We do observe some dispersion of the building demands when we have given a certain value of intensity measures. For example, for the same PGV value, we will have a range of building peak demands that is marked by the red arrows. And this scattering was due to the difference in the ground motion waveform details, which can be attributed to the difference in the amplitude other than PGV that is not captured, and also can be the differences in the frequency content and the duration of the motions. This is best shown in an example where we have the same scatter plot, but only plotted in the linear scale, and we show the 2 cases where they have essentially the same PGV amplitude, but the major difference is that there is our second half cycle that's coming right after the first cycle in case 2. And this leads to about almost 2 times difference in the peak building drift demand. And under the hood, mechanistically, we find this is caused by the fact that the second half cycle pushes the building base towards the opposite direction compared to the building deform state due to caused by the first half cycle. So this exacerbates the building demands. So if we look at the animation, we'll see that when we have a like simple half cycle, this building was get excited, but mostly afterwards is free vibration. But if we go to case 2, after the first half cycle, the building get excited, but at the same time, the second opposite half cycle pushes the base of the building towards the other direction, and this leads to the 2 times larger peak drift demand in the building. We see this phenomenon quite often in the ground motion time histories. In fact, if we define a velocity symmetry ratio, which is essentially a ratio between the two opposite peaks in the velocity time history, and we see that this for motions with higher velocity symmetry ratio, this will typically give higher building peak demands. Either we can see either in the linear space and also in the log space. And this type of peak-related ground motion waveform details can be typically captured by the elastic response spectra, which cares most about the peak response of the structures. And this explains why when we use the spectral acceleration to correlate the peak demands, we typically see a better correlation. And in this case, the bias due to the velocity symmetry is indistinguishable. However, in contrast, we have observed significant uncertainty in the residual drift due to the variability in the input motions. So I'm showing here on the left again the related correlation between the peak drift and PGV. On the right side, it shows the same, but for the residual drift. So compare these two, we see that the correlation between the residual drift and the peak ground velocity is much poor than the peak drift. With also like a standard deviation approaching 1. We have looked at other intensity measures and it shows similar trends. The best correlation we find is between the residual drift and the peak drift. But still the variability in the residual drift, given a certain peak drift, is still large. And we find that this is caused by the fact that the residual drift is not only influenced by the peak ground motion, but also the later wave arrivals. So I'm showing here 2 cases where it has almost the same PGV, also similar waveforms of the velocity time history. But the main difference is shown in case 2, where there is multiple later wave arrivals at the site, and this has led to almost the same peak industrial drift profile across the building height, but very different residual drift. So if we look at the animations, we'll see that this happens because in case 2, the later arrivals has pushed the building towards the opposite direction that partially recovers the residual drift at around 20 seconds. So this leads to the uncertainty in the prediction of the residual drifts. So in terms of post-Earth damage assessments using the residual drifts, so I'm showing here all the data points that we have for the steel moment frame buildings. And also we classify the building damage state based on the peak industrial drift on the horizontal axis and the residual drift on the vertical axis. And this black lines here shows the solid lines shows the FEMA P-58 drift relationship that I showed before, and the dashed line are some simple polynomial fit to the data set. So we see like The FEMA P-58 relation, although it's quite simple, it can capture the central tendency of the residual drift quite well. And if we look at the structures, when we have structures with large peak interstellar drift demands, which typically means the structures are severely damaged. If we use the residual drift as a post-earthquake assessment criteria, we'll see that the percentage of cases when we have large peak drift but small residual drift, it accounts about 11% of the whole population when the building has a relatively large drift. And if we loosen this criteria a bit and consider there could be some residual drift in the structure, but the level of unsafety is not elevated enough, then this still could lead to false negative cases using the residual drift to predict the damage. So we using the data set, we have also done some more detailed statistical analysis. We find that for bin data, the FEMA P-58 relation can capture the tendency quite well, as I shown before. But in terms of dispersion, we find this residual drift demands is better characterized by a wavefront distribution, and this happens for different levels of different ductility levels, and the dispersion level that we see is typically lower than the 0.8 value that is used in FEMA, which is on the conservative side. So in summary, this talk the main takeaways of this talk is SGMD enables us to do detailed building response with high spatial resolution in the near field, and the building peak response is correlated better with the common ground motion intensities than the residual drifts, and this is caused mainly by the fact that the residual drifts are influenced both by the peak, not only by the peak but also the later wave arrivals that happens in the waveforms. And despite the simplicity, the FEMA P-58 drift relation can capture the central trend of the simulation quite well. In terms of the distribution of the residual drift, it's better represented by a wavefront distribution, and there's less dispersion than that specified in FEMA, which can be on the conservative side. And these findings mainly highlight the need to explicitly account for the dispersion of the building drift, residual drift in the seismic assessments. And with that, I conclude my presentation.